delta and this equipotential concepts. And once we are done with this, then we'll come into these segments. So let me explain you this concept of star delta. Okay, see students, this is a Wheatstone bridge actually, right? If you see these questions, but the thing is, in this case, so the bridge is again balanced 2 and 6 product is equals to, again it is your 2 into 6. Suppose instead of taking this value 2, if I make this value 3 now, let's say, okay. Now in this case, if I ask you to find what is RAB, okay, then 6 into 3, 18, and this is 6 into 2, 12. So 18 is not equals to 12. So this is not a balanced bridge. Then how do you find? Because it's a balanced bridge, if it could have been, then it could have removed this 6 ohm resistor, and then it would have been a simple series parallel circuit. You could have solved it. But how do you do in this case? So here is the problem actually. So because we cannot do any star delta, delta star kind of things. I mean to say we cannot do any kind of series parallel kind of things, because so let's say if you are thinking here, the current is getting divided. So once this current is coming to this node and this node, now what way this current will be going where, we are not very sure about it. So in such kind of cases, we come across a situation where we go for the star delta transformations. If we have a star network, we can get its equivalent delta and its vice versa. Okay. So star network is popularly known as Y network. Sometimes this is also known as T networks. Delta network is sometimes known as the pi networks. Okay. So this ZB, ZA, ZC, these three are forming the star. And the outer one, ZAB, ZAC, ZBC, they are forming the delta. So the star delta transformation says a star network, okay, I mean these three. So the star network can be replaced by its equivalent delta or vice versa. If you have this star, okay, of these three registers which is forming a star, you can have its corresponding delta. Or if you have the delta, you can have its corresponding star like this. So both it is possible. Okay. So first, let us see the star to delta transformations, and then we'll see the delta to star transformation. Star to delta, that means star is given to you. Star is given means this ZA, ZB, ZC, these are given to you. And you are converting to delta. That means you need delta. So you need this, and you need this. So based on ZA, ZB, ZC, you have to get this, and this. So the given data is ZA, ZB, ZC. And the required thing what we need is ZAB, ZBC, ZAC. So these three registers or impedance you want to find. Students, so these are some well-defined formula, and it's very easy to figure it out actually. So suppose you want to find ZAB, okay? Its formula is the first suffix, that is ZA, plus the second suffix, that is ZB, plus product of these two, ZA, ZB, divided by the third one. So in the star, you have three things are involved, ZA, ZB, and ZC. So if you want to find ZAB, so it is given by the first suffix, that is ZA, plus the second suffix, that is ZB, plus the product of these two, so that is ZA, ZB, divided by the third one, which is ZC. Similarly, if I ask you what is ZBC, so it is the first suffix, ZB, plus the second suffix, that is ZC, plus the product of these two, that is ZB, ZC, divided by the third one, ZA. Third one means here actually ABC, there are three notations we are using. So AB are here, so third one is C. Here BC are here, the third one is A. Here CA are here, the third one is B. Similarly, if I ask what is ZCA, it is ZC plus ZA plus product of these two divided by ZB. And students, here one thing you can see here, like suppose if I assume that these all value are same. So if I assume that ZA equals to ZB equal to ZC and its value is Z star, let's say. So if you substitute ZA equals to ZB equal to ZC equal to Z star, so what do you get? So you get, this is basically 3 Z star. So you substitute here Z star, Z star, Z star, Z star. So 2 Z star and here 1 Z star will cancel. So it is equivalent to 3 Z star. Okay. So here, if all elements of star are R, okay. then okay, or LLL. I mean, if all these elements are either register or they're either inductors. In these cases, if their value are R, then the corresponding delta elements value will be 3R, 3R, 3R. Or if they're LLL, the corresponding inductors value in delta are 3L, 3L, and 3L. Okay. But in case of capacitor, students, the reverse thing happens. In case of capacitors, if there are C, 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 then it becomes C by 3, C by 3, C by 3. Actually, this you will understand the AC topic, because in AC circuits, so ZC equals to 1 by J omega C, but ZL equals to J omega L. So here, because of direct proportionality, you are getting these 3L factors. So because here ZC case, this is inverse proportional to C. So you are getting the reverse thing, which is happening in this case into 3. In this case, it's happening by 3. So this is what all about is star to delta. Now the next thing is regarding the delta to star. So delta to star means this. These three are known to you. Delta. You need this, and this. So delta to star you need. So how do you do in this case then? So here, so of course, the given elements are ZAB, ZBC, and ZAC. So these are given. And what do you need? You need ZA, ZB, ZC. So these are the required things. So suppose you are supposed to find this ZA. If you want to find this ZA, okay, you see where this ZA is touching this. This is touching here, right? This is the point is touching. So what are connected to these points? ZAB, ZAC. I mean the product of these two, ZAB into ZAC, divided by sum of all the elements of this delta. ZAB plus ZBC, ZAC. So very simple. Again, I'm telling, if you want to get this ZA, okay, you see the middle point here. So this is connected to this and this. So product of this divided by sum of these, and this. So suppose if I ask you what is ZC, so it is connected to this point. So then in this case, product of this and this divided by sum of these, and this. If I ask you what is this ZB, so it is connected to this point. So you need the product of this and this divided by sum of all. So this is what I have actually written. So ZAB, ZBC, ZAC, if you take all these values Z delta, okay, so you get Z square by 3Z, Z square by 3Z. So that happens to be basically Z by 3. So if all elements of the delta are equal, that is Z delta, then all element of the corresponding star are Z delta by 3. So again, because of the direct proportional relation, so if the elements of delta are R or LLL, the equivalent elements in the star are R by 3, R by 3, R by 3, or L by 3, L by 3, L by 3. But in case of capacitor, the reverse thing happens. So it is CCC means it will be 3C, 3C, and 3C. So actually, these are again, there are proof you'll find in the standard textbooks, but anyway, the proof is not required. So I'm not giving you the proofs. Okay, but its applications we are going to see now. Okay, let us see these applications. So with respect to some questions, I want to explain you this. Okay, so in this case, you see that I'm supposed to find what is the value of this RAB. What is the value of this RAB? Okay. So students, see, if some amount of current is coming here, okay. So here, can you tell this answer using series parallel? You cannot tell it, because from this point onwards, the way they are connected, how do you say? You cannot tell actually. Sir, no. So that's why, okay. In this case, the star delta star is useful actually. So what I'm doing in this case is, so this is the corresponding star. So let me convert this into this delta. Okay. So how do you convert? So star having the points you have to locate actually this point, and this point. Okay. These are the points where this star is. So you have to draw a delta between these 3 points. Okay. See, there is a center point, okay, through which all these elements are connected. So we are now targeting this node. Okay. Other than center points, what are the other ends? One end is this one end is this one end is this one. So this is what the star is. So if I convert this to delta, so the delta, one of the element will come here, other element will come here, and other element will come here. So this inner star will be removed and the new delta you will get. So if I do it, so you get a delta here, you get a delta here, and you get a delta here. Because all elements value are 666. If all element value are same in case of star, then in the delta you get 3R, 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 right? That's what the logic says. If all elements value are R, then you get 3R, 3R, 3R. So because here it is 666, so I'll be definitely getting these all value are 18, 18, and 18. So if I do it, so this star I can remove actually. Okay, so I'm removing this star. You see, so this star I'm removing. 1 second. So here was the 2 ohm, right? Yeah. So this is how the circuit is now. And this value was 18, right? So this was 18. So you get this is 18. 6 into 3, 18. And this is also 18. Okay. So I believe we agree that these two are in parallel. So 18 parallel with 18 is 9. In the same logic, 18 parallel with 18, 9. Okay. So this circuits can be drawn as this is 2. This is 18. This is 9. And this is 9. 2, 18. This is 9 and this is 9. 2. Okay. Then you have 18. Then you have 9. And again you have this 9. So this is what your RAB. This happens to be 2 plus 18 parallel with 9 plus 9. You get 2 plus 18 parallel with 18. So 2 plus 9 and that happens to be 11. So the answer of this question was 11. Yes, friends, tell me, is it clear to all of you? Is it clear to all of you, please? Tell me yes or no. All right. So this is what we have done here, the star to delta transformations. Now let us answer these questions. Again, I need to find this R of AB values. So here also the same problem, right? So if you think like current is coming here, so here we are not getting the clear idea like which are in series or parallel. Okay. So what is the benefit actually we got by converting in these questions from the corresponding star to delta? So in the original questions, we are actually clueless actually how do we proceed, because we are not getting any series parallel kind of things. But once we are converting this into delta, now the picture is clear. Then using series parallel combinations, we are able to get the final answer. Okay, students? Yeah, tell me, is this clear or not? The previous question, all of you, please. Don't be a statue, please. Is that clear? If yes, I'll go to the next questions. Okay. So here I need to find this RAB again. Okay. So what I'll be doing is, so in this case, okay. So do you agree that these and these are forming a delta? Because don't say, sir, actually it is not looking at delta. Actually, if I say this is 6 and this is 6, so this diagram is same as the existing diagram actually, right? Because this is the same node, na? So this is a delta actually, right? So what I'll be doing is I'll be converting this delta into star. If I do it, so how do we actually do? So I'll be again marking these 3 points across what this delta is present. Then I'll make a center point. And I'll be drawing 3 registers. One registers will come here, other one will come here, and other one will come here. Okay, na? Now, because all elements of delta are same, okay, so all element of the star will also be same, but in this case, by 3, by 3, by 3 will get. So 6 by 3 is 2, 2, and 2. So if I've done it, I can replace it now. This is a problem actually. Okay, anyway. Okay, now see. So now it is, like we have read on the circuit this way. So if I ask you what is R of AB, so in this case, 6 and 2 are in series, 8 parallel with 2 plus this is 2. So 16 by 10 plus 2. It is 1.6 plus 2. So this happens to be 3.6. So the answer is 3.6. So because I'm using a what? A smart board. So I'm able to edit in this case, in this one only. But you being a student, you please draw the separate circuits. Okay. So the answer is 3.6. In the same way, here I can have the delta. I can have the delta like this. Okay. So all elements of the star are same. So I can have the delta. Okay. So this is 6, 6, and 6. 6 parallel 6 is 3. 6 parallel with 0 is 0. And this is 6. So this can be redrawn as this is 6. This is 0 means it is sorted path. And this is 3 ohms. So this is 3. This is 6. And this is 0. So now this is R of AB. That happens to be 6 parallel with 3. And that happens to be 2 ohms. Okay, na? So this answer is 2 ohms. Hopefully all of you are getting the same answer, 2 ohms. Fine. Okay. Now let us take up the next questions. Okay. It's a breeze, but not a balanced breeze. So how do you get? Okay. So the same story. So this is your 666. This is forming a delta. You can also make arguments that this is also forming a delta. But for ease of calculations, I'll be interested to take this one as my target, because if I take this one, then I have to get involved into the calculations, which I don't want to. So how do you get? So you highlight these nodes: this node, this node, this node, and this node. So 3 registers you can draw. You can draw like this. So this value is 2, 2, and 2. So now if I ask you what is R of AB, so this happens to be 2 plus 2, 4, 3 plus 2, 5. So 4 parallel with 5 and in series with 2. So 20 by 9 plus 2. So this happens to be how much? 38 by 9. So 4 point something you will get. This is the answer. Okay, this is the answer. Okay, one more concept I want to explain you. For that, let me take a balanced bridge actually. Okay, so it's a balanced breeze. So let me take this value as 6, 6, 6, 6, 6. Intentionally, I have taken equal value, but There is no such restriction actually. See, actually, I hope you know this, but I want to again brief it. So actually, what happens when the bridge is balanced actually? So when the bridge is balanced, okay, remember, we always say when the bridge is balanced, that means the current in this galvanometers, when we connect it. So when the bridge is balanced, it means actually this point and this point are the same potential. If this point and this point are the same potential, so definitely this current will be zero, because you know by Ohm's law you can find this current. So this current will be nothing but the voltage by resistor, voltage by this 6 ohm resistor. Now what is the branch voltage? Branch voltage difference of the node voltage. Now if I say this node voltage and this node voltage are same, it means the branch voltage is zero, because if I want to find the branch voltage difference of this and this node voltage, so branch voltage is 0, 0 by 6, that becomes 0. That becomes 0. Isn't it? But friends, remember, whenever you know 2 points are at equipotential, okay, when you know 2 points are equipotential, that means I'm saying that's a balanced bridge. So in a balanced bridge, what happens is these 2 points are at same potential. We say these are equipotential points. So whenever you get equipotential case, okay, then the element between those 2 points can be replaced by any other elements. It can replace by a 5 ohm resistor, a 3 ohm resistor, a open circuits, or a short circuit. Doesn't matter actually. I mean to say, this circuit is equivalent to either you can replace this 6 ohm by open circuits, which we very frequently do, or you can replace it by short circuits. If you replace it by short circuits, it will look something like this. Okay, or you can replace it by any other resistors. It really doesn't matter actually. Okay, so in this case, if I ask you to find the equivalent resistance, 6 plus 6 is 12, 6 plus 6 is 12, and these two are in parallel. So 12 parallel 12, you get 86. This case, 6 and 6 are in parallel, you get 3. 6 and 6 are in parallel, you get 3. And I believe we agree that this and this are in series. So again, if you try to find the equivalent resistance, this happens to be 6 ohms. So both of the cases, we are getting the answer as 6 ohms. Both of the cases, we are getting the answer as 6 ohms. Okay. So students, actually, okay, so this is what one concept I said regarding equipotential point. The point you want to remember, you should remember is, once you identify 2 points are equipotential in circuits, the element which is connected between those 2 points can be replaced by a short circuits, or by open circuits, or by any other. It really doesn't matter actually. Okay, as per our convenience, we replace it by open circuits, short circuits, or if you are connecting this by a 10 ohm resistor, still there is no problem. But generally, most frequently, we do short circuit, open circuit for ease of calculations. Okay. But the next point is, how do you know which are equipotential points in a circuits? So actually, this is basically some common sense I can say. See, what you assume is, you assume that some amount of current is coming to this node. Okay. Now, when some amount of current is coming to this node, okay, so there are 2 paths. And if you see, this path are identical path actually. How do I say this identical path? Okay, opposed from this point. So this path and this path are looking identical or not? When I say identical, this is something with respect to the resistor's value. That means if I observe, if I scan this path, so it is like 6, and then it is getting divided into 2, 6, 6. And here also, if I see 6, and again it is divided into 6, 6. So that way, the circuit is looking symmetrical from this point onwards. Okay, so whenever you get, the circuit is symmetrical, the current get divided into 2 parts, because this I is coming here, and there are 2 identical paths. This path and this path are identical. So definitely, this current will be your I by 2, and this current will be your I by 2. Okay, I amount of current is approaching to this node, and this I is getting divided into 2 parts, I by 2 and I by 2. Okay. Now, don't you think by this logic, these points will be equipotential. Why? Because if the current is I by 2, I can get this voltage, which is 6 into I by 2. Even this voltage is same. Now imagine a case, if I say this node voltage is VA. Now if I ask you what is this node voltage, this is VA minus drop of this. Similarly, what is this node voltage? VA minus drop of this. The point is, because the paths are identical, this current will be getting divided equally. And when the currents are getting divided equally, these drops will be same because their value are same. And the drop is same, this node voltage will be definitely same because this node voltage is this node voltage minus drop of this. Similarly, this is this node voltage minus drop of this. So these 2 points are equipotential points. In the same way, students, here I want to actually highlight. So if I ask you, what are the equipotential points in these cubes? So if you see, okay, so the current Ix is approaching to this node, okay. Now here there are 3 identical paths. This path, how do I say identical path? R followed by RR. R followed by RR. Okay, R followed by RR. The paths are identical actually. So when the paths are identical, the current will get divided equally. So when the currents are getting divided equally, the drop of this, and drop of this will be same. So what is the consequence of it? Then the consequence is this point, and this point drop will be same. I mean, the potential of this point will be same. Why? Because this point potential is this point voltage minus drop of this. Similarly, if I ask you what is this voltage, then this voltage is nothing but this point voltage minus drop of this. What is this voltage? Then it is basically this point voltage minus drop of this. Because I know the currents are same in this, and this. So the drops will also be same, right? So definitely these 3 points will be at equipotential. So if I highlight it, so this point, this points, and these points are at equipotential. Okay. So if I connect any element between these points, so that can replace by any of the short circuits or open circuit or whatever it is. Now, that's all. Is it like only equipotential point or there are something else? There are something else as well. How there are something else? Because as we said, so like the current Ix by 3 was going. At this point onwards, these currents were again getting divided into this and this. Similarly, this and this. So I believe you agree that the potential of these points and these points, okay, and these points will be same. Suppose, for example, if I ask you, what is this point potential? So this point potential is this point potential minus drop of this is this point potential. Okay, so that means if I highlight it, okay, so this is one point. I'm highlighting a different okay color. So this node potential is basically this node voltage minus drop of this. Similarly, this point potential will be this point potential minus drop of this. Okay, in the same way, this point potential, okay, if you see, is basically this potential minus drop of this. Now, because this drop, and this drop will be same because the currents are X by 6 and the value of resistors are same. So it means these 3 points are also equipotential points. But whether this set and this set potential will be same? No. I'm saying that this value are same. This value are same. I'm not saying that this value and this value are same. I'm not saying that. That's why I'm highlighting in different color pen. Question which is asked in the recent year papers, which is in electronics, and which is where it gone. Well, yeah, this is the questions which are asked in GATE 2018. Okay. So what is given? Value of R1 is 1, R2 is 2, R3 is 3. So the network is connected to a constant voltage source of 11 volts. The magnitude of current through the source is how much? So what is the current? So they're asking. Now let me take it to the other page. Okay. My target is, so what is asked actually? So in the questions, we are supposed to find what is the currents. This is what we are supposed to find. So what I'll be doing is, so this segments, I'll be replacing it by its equivalent resistance. If I do it, then this circuit will be replaced by, this is 11 volts, and this is your R equivalents. And this current, the I, what you want to find, so this I will be given by 11 divided by R equivalents. Okay, I will be given by the voltage source divided by this equivalent resistance. Okay. Tell me, equipotential concept is clear to all of you or not? Respond me. In the questions, they will not be mentioning you solve it using this method, that methods. You never get like that. You have to use your brain correspondingly, the way the questions will be framed. Okay. Let us see. In this case, okay. So if the concept is not clear, let me know. I'll explain it again. But if you are silent, I'm getting confused. So here actually, how do you find this I actually? So please, I mean, like when I'm asking something, you please respond me. Otherwise, if it is one-sided case, then I will have no options other than skipping the good concepts. Okay, I'll do that if you not respond when I'm asking you. So if I'm teaching something good and not if it doesn't matter to you, then why should I spend so much of energy? Tell me, yes or no? Anyway, ultimately, I'm teaching it for you, not for me. So you should respond when I'm asking you. Okay. See, so the challenge is to get the R equivalent of this complicated structures. Now, if you see this I amount of current is approaching to this node. And here, do we agree like the circuit is looking symmetrical? Why? Because this path, if I observe, it is R1 followed by R2, R3, R1. This path, if I follow, R1 followed by R2, R3, R1. So yes, this path and this path are identical paths. So if this and this are identical path, it makes sense that this point and this points are equipotential points. In the same logic, this point and this point are also equipotential point, because if I observe from this way and this way, so it is R1 followed by R2, R3, R1, R1 followed by R2, R3, R1. So yes, the circuit is looking symmetrical from this end as well as this end. So these two are symmetrical point. These two are also symmetrical points. So what we said, in the sense, if a element is connected between two equipotential point, that element can replace by short circuit or open circuit. So here only for convenience, so I'm just replacing it by short circuits. So this R2, I'm replacing it by short circuit. Okay. So this R2, I'll replace it by short circuit. In the same logic, this is also replaced by short circuits. Now, if you see, if these are replaced by short circuits, I can easily redraw these corresponding circuits. So if I redraw this circuit, so how does this will look like? How does it look like in the sense? So this is the node from here. So this is the node A. If I say this node is A and this node is B, so this is the node A. Okay. So this is not A actually. This is what? And this is the node A actually. Okay. And from this point to A, you have two resistors whose value are what? R1 and R1, like this. Then between A and this is your B. Between A and B, what are connected? This is between A and B, because if this node is A, this node is A. If this is B, this node is also B. So this R1 is between AB This R3 is between AB. This is also between AB. This is AB. That means these four are between AB. So this is between AB. Okay. And then you have again R1 and R1. These two. Because once you are sorting it, it's a same node, right? It's a same node. So these two R1 are between this node and B. So this node and B. These two R1 are between this node and A. So this node and A. So this value is R1, this value is R1. And here it is R1, R1, R3, and this is also R3. So what is your R equivalent then? R equivalent is, so R1 and R1, they are in parallel. You get it is R1 by 2. R1 and R1 in parallel, you again get it is R1 by 2. And I believe you agree that these and these are in series. So equivalently, this and this will become R1. Okay, but what about this? So this is R1, R1 parallel, you get it is R1 by 2. R3, R3 parallel, you get this is R3 by 2. So R equivalent is, so combination of this and this is R1 plus R1 by 2 is in parallel with R3 by 2. R1 by 2, this is in parallel with, I mean R3 by 2 in parallel with R1 by 2. You can substitute the value of R1, R2, R3 which are given. R1 is given 1, R2 is given 2, and R3 is given 3. Right? This is 1 plus 1 parallel with 3 by 2. So this happens to be 1 plus, this is 3 by 2 divided by 1 plus 3 by 2. This is 1. If I multiply 2, this is 3, this is 2, and this is your 3, which is 1 by 3 plus 5. So this happens to be 5 plus 3 divided by 5, and that is becoming 8 by 5. 8 by 5. But some mistake is happening. What is the mistake? Anybody? R1, R2, R3 value are given 1 to 3, right? R1, 1, R2, 2, R3, 3. Then R1 is, acha, yeah. This is R1, right? This is 1 actually. This is 1. Yeah. Okay. So in that case, so these are calculations will be wrong. Yes. Okay. So then this happens to be 1 plus, this is 3 by 4 divided by 1 by 2 plus 3 by 2. This is 1 plus, we multiply 4, this is 3, this is 2, and this is 6. So 1 plus 3 by 8, that happens to be 11 by 8. Yeah, this is what I was looking for. So R equivalent is 11 by 8. So I happens to be 11 into 8 by 11. 11 cancels, so answer is 8 amperes. So 8 ampere is the right answer. Okay. And I believe you can easily answer this problem, right? This is a simple delta to star transformations. So what is the, in the given circuits, each register has value 1 ohm. So all these register value are 1, 1, 1, 1, right? So what is the equivalent resistance between AB they're asking? You can find it or not. you have to convert this inner delta into star. So if you convert into star, you get a big star. Okay. Then that star you have to convert into delta, and then if you convert to delta, then you get the thing in the series parallel form. If you simplify it, the answer should be 8/12. So I think this also you can easily answer. Okay, what they're asking. So they're asking the equivalent resistance between AB. So you see, this is a balanced breeze or not? Yes. This also a balanced breeze, and this also a balanced breeze. Why? R square, R into R equals to R into R, R into R, R into R, R into R, R into R. So because there are three breezes and they are connected in cascade this way, so and all of them are in balance. So we can replace this bridge element by either short circuits or open circuit, doesn't matter. So let us say that I am replacing it by short circuits. So this is what the situation is. If it is short circuit now, so R and R, this is parallel. You get here, this is R by 2. In the same way, you get R at R parallel, you get R by 2. Again, I hope you agree, like this point, and I mean, these two resistors are connected between this point and this point. So this and this in parallel. So you get it is R by 2. And this in parallel, you again get it is R by 2. Here also you get it is R by 2. Here also you get this is your R by 2. And again, this R by 2 and R by 2, these are in series. So if these are in series, I mean to say, this path which I am showing in green is series combination of R by 2 and R by 2 is R. This segments, which is again series combination of R by 2 and R by 2 is again R. And this segments is how much? R by 2 and R by 2 is again R. This segment basically. R by 2 and R by 2, they are in series. We get this is your R. So now if you see from here, there are three registers actually. One is this entire thing we replace by R. This also R and this also R. I mean R, R and R. So these three are in parallel. So R equivalent is R parallel with R parallel with R. So if R parallel with R parallel with R, so that is your R by 3 because R is given 300. So 300 by 3. So that becomes 100 ohms. So 100 ohm is the right answer for this problem. Okay, right? So this is what the solution of this problem. So like this, every year you find a questions from this segment. So you see this question also you can easily answer. Question number 31. For the Y network shown in the figure, the value of R1 is how much? So this question is based on directly formula. You know what? Your star to delta. Star are given, we need the element of this delta. So if I denote this by the node A, this by node B, and this by node C, this is my RA, this is my RB, and this is my RC, and this is my RAB, which is R1 in this case. So RAB is given by the formula RA plus RB plus product of these two, which is RA RB divided by RC. So RA value you can substitute, which is 5 plus 3 plus 15 divided by 7.5. That is 5 plus 3 is 8 plus 2, that happens to be 10. So this answer is 10. So like this, some simple questions are also there. Okay, this also you can easily solve this 25. Okay, you try this 25th. This you can easily solve. This a Y network has Y network means what? What is the meaning of Y? Y means star. I told you, right? A Y network has resistance of 10 ohm in each of 2 yards, and while the third one has a resistance of 11 ohm. So they're asking in the equivalent delta network, the lowest value among the three resistance is what? You can do it or not. So what is being given? So there is a star network. In the star network, 2 arms resistance are 10 and 1 resistance arm is 11. So this is 10, 10, and 11. They're asking if you're converting this into delta, what is the minimum value of this delta registers? You'll get 3 registers or not. One you get here, one you get here, and one you get here. So among these, and this, which is the minimum one? Directly you can make use of the formula and you can get the answer. So like this, there are countless number of questions based on these all concepts. All right. So this is what we mean by the star delta and equipotential concepts. Now, this is the time to go with this second category, which is how to find the equivalent resistance in the presence of the sources. In these cases, you have seen, like the register segment, what we are considering, it was not involving any kind of sources. It was only purely registers. But in this case, if the sources are present, how do you handle the situations? There are 3 cases: only dependent source, only independent source, both dependent source. Friends, remember, in the next topic, while teaching you the Thevenin-Norton theorems, I will not teach how to find RTH and RL. So this is what is the exactly same thing. Okay, finding the equivalent resistance is also equivalent to finding the Thevenin resistance, or also equivalent to finding the Norton resistance. In the theorem topic, whenever somebody will ask you find the Thevenin Norton resistance, so these all things you have to do. So I have shown all these cases. If there are no sources, now we'll see if there are sources present, how do we handle it? Okay, so I have taken some questions. So one by one we'll see. So the method is very simple actually. Okay, the method is, there are 3 cases I said. The case 1, I said only dependent source. So if it is only dependent source, so what is the method? In this case, the method is connect a test voltage source, not necessarily voltage source, but generally we go with voltage source, VT, and let its current is IT. Then in this case, you get the value of RTH as the ratio of VT to IT. Second case, if it is containing only dependent source, only independent source. If it is containing only independent source, so replace each voltage source by short circuits, replace each current source by open circuits, then do series parallel reduction. This is how you do if it is only independent sources. Third case is, if it is containing both independent and dependent sources. Okay, the first point is, so replace all independent voltage source by short circuits, current source by open circuit. This is the first point. Next point is, do not disturb dependent source. Okay, now your RTH or R equivalent, whatever, is ratio of VT to IT. So this VT to IT is something same as this one. Okay, so let me explain you these all concepts by one. Okay, so let me come into this category. So if you see, this network is containing some sources, but this is containing only independent sources. In other words, there are no dependent sources in this network. It is only independent sources. What is the statement I said? In the only independent source, replace each voltage source by short circuits, each current source by open circuits, then do series parallel reductions. So what I'll be doing is, so this current source, I'll be replacing it by open circuits. So this current source, I'm replacing it by open circuits. This voltage source, I'll be replacing it by short circuits. Okay, and I'm supposed to find the resistance from AB terminal, so I'll find it. So from here. Now, if I find from here, so I hope you agree that these two are in parallel. And then overall it is series with this, and this. So if I ask you what is your R equivalent, which is same as R Thevenin, which is same as Rn, okay, this is given by 2. This is given by 2 plus 2.5 plus 3 plus 10 parallel with 30. 2 plus 2.5 plus 3 plus 10 parallel with 30. So this is 7.5 plus 300 by 40. 300 by 40 is how much? 30 by 4. 30 by 4 is 7.5. This is coming 15 ohms. So the answer to this problem is 15 ohms. So this is how you deal with the circuits if it is containing only independent sources. If it is containing only independent sources, voltage sources short, current source open circuits. Then if you are replacing voltage source short, current source open circuit, then the network will contain only resistors. Then you do series parallel, or it may, if it is needed to do delta star transformation, you may make use of it as per the circuits, and you can get the equivalent things, which is coming 15 in this case. So this one we have taken. Now coming to only dependent source, what it says, connect a test voltage source Vt and let its current It, then Rth is Vt by It. So let's say in this case, I'm supposed to find the resistance from this particular terminal. So what I'll be doing is, so let me connect a test voltage source, which is Vt, and because of it, the corresponding current is It. So now you have to get this Vt to It ratio. So here I can see this current and this current are same. That means this is your It, similarly this is your It, right? Because this is same currents. Now here at this node, if I see, so this current is basically Vt by 4, and this current is basically Vt minus 2It divided by 2, right? Because if I take this point is ground, I can tell this node voltage is Vt. So what is this? What is this current? This current is this branch current. This branch current is this branch voltage divided by 2. So what is this branch voltage? So this node voltage is Vt. This node voltage is 2It. So the branch voltage is Vt minus 2It, and the current is the branch voltage by 2. So now I can write the KCL at this junction. If I write the KCL at this junction, I get incoming current is It is equals to outgoing current is Vt by 4 plus Vt minus 2It divided by 2. Let us multiply 4 both sides. So you get 4It is equals to Vt plus 2Vt minus 4It. If you see, 8It is happening to be 3Vt. So your Vt to It ratio is happening to be 8 by 3 ohms. So the value of Rth or R equivalent is basically 8 by 3 ohms. So this is what the method is. So whenever you get a circuit which is containing only dependent sources, connect a test voltage source like this and try to get the ratio Vt to It. So once I have connected this voltage source, the corresponding voltage and the current is Vt It. And then, so my intention is just to get the ratio of Vt to It. So then by targeting this Vt It, so I got this current Vt by 4. I got this currents. Then by writing a KCL here, I'm getting this answer. Okay, na? Similarly, this question is asked in GATE 2012. This I'm giving it a task to you. You simplify this, the answer is supposed to be 50 ohms. So this is also containing only dependent source. If it is containing only dependent source, what is the method we said? The method is what? You have to connect a test voltage source here. So this is your Vt and this current is It. So you can get the value of Vt by It. So that will be coming 50 ohm in this case. So this I am leaving a task to you. And this is the last one. So this category is containing what? It is containing independent sources as well as dependent sources. In this kind of cases, what is the method I said? The method I said is if it is containing both independent and dependent source, replace all independent voltage source by short circuit, current source by open circuit. That means you are supposed to make use of these two steps again. Do not disturb the dependent source. So dependent source should not disturb. And then again, you proceed the way we have done the first case. So then you can get this RTG equals to VT by IT. So what I'll be doing in this case, the dependent source which are present, so it should be replaced by corresponding short circuit, which is voltage source, open circuit, which is current source. So this was the current source. Current source, I'm replacing it by open circuits. This was the voltage source. So voltage source, I'm replacing it by short circuits. Okay. Now, dependent source should not be disturbed. And then what I said, because I need this RAB, I'll be connecting a test voltage source whose value is VT and the current is IT. And in this case, the value of RTH will be the ratio of VT to IT. Okay, fine. So let us take this point is ground and try to see how to get the value of VT by IT. So this also you can do it, right? But let me do this problem for you. So that is, what I can do is, so this current is IT, okay? Nodal analysis, actually, I haven't taught you. That will have been the best way to solve such kind of problem. Anyway, so what is Vx? So Vx is this branch voltage, and there's nothing wrong if I say this is what is my Vx, because if one end of the branch is connected to ground, then the branch voltage will be same as the node voltage. So this is your Vx. But what is Vx? So this voltage Vx is this voltage Vt minus 30 IT. So your Vx in this case is your Vt minus 30 IT. So this current is Vx by 15. And this current is Vx minus Vx by 3 is how much? 1 minus 1 by 3 is basically 2 by 3. That is 2 Vx by 3 by 10, that means 30. This node voltage is Vx minus Vx by 3. So Vx minus Vx by 3 is basically 2 Vx by 3. So 2 Vx by 3 is this voltage, and you need the current, right? So by 10. So 2 Vx by 3 by 10 is 2 Vx by 30. So we can write the KCL equation at this junction. If I write it, I get the incoming current is IT is equals to the outgoing current is Vx by 15. So in place of Vx, let me substitute Vt minus 30 IT divided by 15. And this is 2 Vx by 30. So this plus, because this is what is the only incoming, these and these are outgoing. So that's why incoming current equals to sum of outgoing currents. So 2 Vx by 30. So it is 2 Vt minus 60 IT. That is because you need 2 Vx divided by 30. If you multiply 30 now, both equation, so 30 IT is equals to 2 Vt minus 30 IT plus 2 Vt minus 60 IT. Okay. This and this, if I collect it together, that is how much? 90, 30, 120. 120 IT is equals to 4 Vt, right? Because this and this are 4 Vt. So Vt by IT ratio. So Vt by IT ratio is how much? 120 divided by 4. Yeah. So RTH value is coming as 30 ohm in this case. The answer is 30. So nothing to worry actually. So as you progress the nodal analysis method, so these all equations will be again very straightforward to go with. But I believe you, like just by using the Ohm's law and KCL, so I'm just finding these all solutions. So the answer is 30 ohm for this. So this is how actually you deal with if the network is containing both independent as well as dependent sources. And with this, the concept of the resistance reduction technique is completed, right? This segment I have said. So this is what it is completed. So I have taken a good amount of time to explain this, right? So if you see this list of the first chapters, so we are left with the last concept, which is mesh and the nodal analysis. So let's go for a 10-minute break, and after the break, we'll learn this mesh and nodal analysis. All right. Yeah. Fine. I'll come back after a 5 minutes of break. Okay. Now let us say this, the next concept, that is mesh analysis and nodal analysis. So students, actually, like these are two systematic methods to solve the network problems. So far, whatever the number of questions I have taken in this particular chapters, mostly they are of there is no systematic way. I'm saying that this is the branch voltage, this is the branch current, this current will go this way, that current will go that way. So like this, based on the inspections or based on the experience only, we are solving the questions. Or I haven't given any kind of systematic methods, like using this, you can get it like that, right? So these are two systematic methods using what you can solve the networks. Okay. So in mesh analysis, we make use of KVL and Ohm's law. So KVL plus Ohm's law is mesh analysis. The minimum number of mesh equation needed to solve a network is B minus N minus 1. B is the number of branches and N is the total number of nodes. So total number of mesh equation need is B minus N minus 1. Okay. By finding solution of mesh currents, we can obtain any branch currents by KCL at nodes, hence voltage as well. I'll explain what is the meaning of these statements. Now directly, let me jump into the problems. So I want to explain you the concept of mesh analysis through the questions. Okay, this is the questions, and the question is find each currents and voltage of the registers. So whatever the number of registers you have, okay, so you have to find the currents of them. Okay, the method is something like this. The method is, so what is the mesh? Mesh is a closed path which does not have other closed path. So you have three meshes here. So this is my mesh 1. This is my mesh 2. This is my mesh 3. Actually, there is no point to write M1, M2, M3. So actually, these are the three meshes, M1, M2, M3. And these are the corresponding mesh currents, I1, I2, I3. Okay. So what you do is, so this is what the mesh current. So these currents are circulating in the clockwise. Always, students, remember. So you can take anti-clockwise also or combination of them as well. But to avoid confusion and mistakes, it is always stick into a standard conventions, and most frequently we stick into clockwise. So I have taken it in clockwise directions. Okay. So this current is circulating in this mesh. This current is circulating in this mesh. This current is circulating in this mesh. Okay. Now, so see here, let us do one thing. So I know this current is I1 actually, right? This current is I1. And I know this current is I2. So if you see, this is actually I1, right? Yeah. If you see, I1 amount of current is coming here. Okay, I2 is going this way. If I ask you what is this branch current, so this branch current is I1 minus I2. In the same way, if you see, I3 amount of current is coming here. So this current is my I3. So if I ask you, this current is I3, this current is I1. So what is this current? So this current is basically your I3 minus I1. If this is I3 minus I1, then this current is your I1 minus I3. This current is your I1 minus I3. So the point what I want to highlight in this case is, if I am moving in the clockwise directions in a mesh, okay, the registers which is not shared with any mesh. So this 2 ohm is not shared with any mesh, but the 6 ohm is shared between these two mesh. This 10 is shared between these two mesh. This 8 is shared between these two mesh. Okay, like this. This 1 is not shared by any mesh. This 4 is not shared by any mesh. This 2 is not shared by any mesh. Are you following or not? So if I'm moving in the clockwise directions of the mesh, the currents where the registers is not shared, you get the same mesh current. But if you get a register which is shared between two mesh, so that current is the mesh current which you are taking about I1 minus the other mesh current. So you are moving in the direction of mesh 1 current, right? So you are moving in the clockwise directions, and this is the reference current of this I1. So the registers what will come across, okay, which is not sad, you get I1, which is sad, you get I1 minus I2, which is sad, you get I1 minus I2. In the same way, if I am going like this, so this current will be I2. This current, if I ask you, this will be your I2 minus I3, not I3 minus I2. I2 minus I3, and this current will be your I2 minus I1. It makes sense, right? If this current is I1 minus I2, so this will be definitely your I2 minus I1. This current is definitely your I2 minus I1. In the same way, if this is I3, so this current is I3 minus I1, this current will be I3 minus I2, and this will be I3. So the moral of the story, what I want to say is, if you are taking a current as reference and if you move across clockwise, so the registers which are common between two mesh, so in that case, the current will be that mesh current with respect to what you are moving, that is I1, minus the other current between what it is sad. So here, if I'm taking the reference of I1, so this current is I1 minus I2. But if I'm taking the reference of I2, so this current will be I2 minus I1. Similarly, if you see, if I'm taking the reference of I1, this current is I1 minus I3. But if I'm taking the reference of the third mesh current, this will be I3 minus I1. So this is the point, it should be kept in your mind. Okay, you see how I am making use of this concept to write the mesh equations. Then I'll tell a shortcut actually. Okay. So how do you write the equation means? So here, for the first mesh I'm writing. So the KVL I'm writing. So here, minus 2 plus is 1, minus 2I1. Here 2I1. Then minus of 6 into I1 minus I2. Minus of 10 into I1 minus I3 equals to 0. Okay. 1 minus 2I1 minus of 6 into I1 minus I2. Minus of 10 into I1 minus I3 equals to 0. Again, 1 minus 2I1 minus 6 into I minus I2 minus 10 into I minus I3 equal to 0. This is what the equation of the first mesh. In the second mesh, if you write, I mean this mesh, so I'm starting with here. So minus 4I2, minus 7, minus 8 of. Now it will be I2 minus I3, please, not I3 minus I2. Minus 6 into I2 minus I1 equals to 0. Similarly, for the third mesh, if I write it, okay. So for the third mesh, what do you get? For the third mesh, if you see, okay. So here, how do you move? So I'm moving in the clockwise direction. So I'm moving in the clockwise directions. So like this, I'm moving, right? So 15 minus 10 into, now it is I3 minus I1 minus 8 into I3 minus I2 minus of 1 into I3 equals to 0. Okay. So now I think you can easily solve these three equations. And based on this, you can get the value of what? This I1, I2, and I3. And if you simplify these all equations by arranging these all things, the answer you're supposed to get is I1 is 1.5, I2 is 1, and I3 is equals to 2. So this you can verify later. This is what the solution are going to get. Okay, so three mesh current mesh equation I have written, one for this, and this. So if I'm writing for this, again the same story. KVL means minus 2 plus means plus 1. So here minus 2 I1, here minus 6 I1 minus I2, here minus 10 I1 minus I2. Because I'm writing for mesh 1, that's why you are getting I1 minus something, I1 minus something. But if you write the same 6 ohm for the second mesh, you see you are getting I2 minus I1. And if you write the 8 ohms for this second mesh, you get I2 minus I3. But if you write this for the third mesh, you get I3 minus I2. So if you're writing for mesh 3, I3 will always come first. If you're writing for mesh 2, I2 will always come first. If you're writing for mesh 1, I1 will always come in first. So this is what the solution is. Okay. So students, actually there is a shortcut actually. Okay, I want to explain the shortcuts. Okay, so see, the shortcut is something like this. So I'm defining some term known as self-resistance and mutual resistance of the mesh. Okay, so what I'm doing is left hand side will contain self resistance term. This will be always positive sign, and mutual resistance term, this all will be the negative sign if it is the left hand side of the equations. Right hand side will contain only the source. If the source is from plus to minus, I'll take negative sign. If source is from minus to plus, I'll take it as positive sign. Okay. Now, what is the meaning of this? You see. Suppose for mesh 1, if I ask you what is the self-resistance? Self-resistance means sum of all the resistors which are in the mesh 1. So mesh 1 resistance is 2 plus 6 plus 10 is 18. Okay. And mesh 2 self-resistance is 6 plus 4 plus 8. Mesh 3 self-resistance is 10 plus 8 plus 1. These are the self-resistance. So if I'm writing the mesh equation for mesh 1, the equation will be, you see, left hand side will contain the self-resistance term, the sign is positive. Mutual resistance term, the sign will be negative. So what is self-resistance of the mesh 1? 2 plus 6 plus 10, that is 18. So you get plus 18 into I1. That's what I'm saying. Self-resistance term signs should be positive. Mutual terms are negative. So here it is 6. It's a mutual resistor because this is between two mesh. The resistor which are between two mesh, I'm saying it is mutual resistance. So here it is 6, here it is 10. So this sign will be negative. So you get minus 6 into I2. Because this is shared with mesh 2, I'm getting I2. Minus 10 I3. Again, it's a 10 is mutual. So which is shared with mesh 3. So I'm getting I3 is equals to. Now you move in the clockwise directions. If you're moving in the clockwise direction, minus to plus means positive. Minus to plus means positive. Plus to minus is negative. So minus to plus means it is 1. So this is 1. Mesh 2, if I ask you, okay. So sum of the self resistance 8 plus 6 plus 4 is 18. So you get plus 18 I2. And for the 6, you get minus 6 I1. And for 8, you get minus 8 I3 is equals to minus of 7. So 18 I2, okay, minus 6 I1 minus 8 I3 is equals to minus of 7. Similarly, for mesh 3, if you want to write, how does the equation will be? So 10 plus 8 plus 1, that is 19 I3 minus 10 I1 minus 8 I2 is equals to plus 15. So these are the three equations. In fact, I mean to say, if you are simplifying these all equations, okay, that is this, this, and this. So these are what the answer you're going to get. You can verify it. This is the answer. Have you understood the shortcut? Have you understood the shortcut or not? Tell me. Okay. So this is how it is. And coming to this case, in this case, if you see, so again, let's say this is my mesh 1, this is my mesh 2, and this is my mesh 3. I mean, again, you should be writing I1, I2, I3, right? Okay. Have you understood the shortcut? Shortcut is understood or not? Or doubt? Okay. So for mesh 1, by shortcut method, if I write the equations, so 4 plus 1 is 5. So 5I1. This is mutual with I2. So you get minus of 1 into I2. For this, it is mutual with the third one. You get minus of 4 into I3 is equals to, if you are moving in the clockwise directions, plus to minus. Plus to minus means negative sign. So you get here it is minus 17. Similarly, for mesh 2, if you write, for mesh 2, the self-resistance is how much? 1, 3, 2. So 6. So you get plus 6I2 and minus of 1 into I1, minus of 3 into I3 is equals to how much? Plus 70, right? So 1, 3, 2, 6I2 minus of 1 into I1, minus of 3 into I3 is equals to, it is minus to plus means it is positive, that is 70. So this is the second equations. And students, third equations, if you see in the mesh 3, okay, actually our goal is what? My goal is to get all voltage currents, right? So basically my goal is to first to get the mesh currents. And you see in this mesh 3, so this current I'm saying the I3, and don't you think I3 equals to 1 ampere? Because in the mesh 3, there is a current source which is in the outer boundary. And I can see if I'm saying the mesh current, I3, so I3 is this current. Now, don't you think I3 is 1? Yes, I3 is 1. So directly in this case, I'll be writing I3 equals to 1. No need to write this one because directly mesh current is known to me. So these are what the equations. In fact, in these two equations, you can substitute I3 value is 1. So if you substitute I3 value is 1, so this will be constant and you have only two equations containing two unknown I1, I2. You can easily simplify them. And if you solve this, the answer what you're supposed to get is I1 is minus 2. The value of I2 is coming 3. And the value of I3 is, of course, it is 1. Okay, so this is what is the answer you're supposed to get if you simplify this set of equations. But students, actually, this question is incomplete. I left in between. I told you what I told you. I told you to find all branch currents, right? So that's what was the question. So I just left in the what by finding this mesh current. So let us find it. So this current is I1, which is given 1.5. So I'm moving in the direction of I1 mesh current reference. So this current which I highlighted now, so this will be definitely I1 minus I2. So 1.5 minus 1, which is basically 0.5. This current is I1 minus I3. So 1.5 minus 2 is basically minus of 0.5. So this current is minus of 0.5. Now this current is I2. What is I2? I2 is 1. This current is, I'm moving in the direction of I2. So it is I2 minus I3. So 1 minus 2, you get it is minus of 1. Okay. Similarly, this branch current is I3. So if I move in the direction of I3, so you get this is 2 ampere. Now you see all the branch currents I obtain. All branch current I obtain. If you know all branch currents, you can get all the branch voltage, right? Because I into R you can do. So you know all branch current, you know all branch voltage, then you can easily find the node voltage because branch voltage is difference of the node voltage. That way you can proceed. So all the solution is known to you now. Once you have the mesh analysis, all the solutions in your hand. Here also it is same story. The value of I1, I2 and I3. So I1 will be minus 2 is set. So this current is minus 2. This current is anyway, this is 1 ampere. Now if I ask you what is this current, so if I'm moving in the direction of I1, it is I1 minus I2. So minus 2 minus 3, this current will be minus of 5 amperes. What is this current? Actually, I did a mistake. This is between I1 and I3, right? So it is I1 minus I3. So minus 2 minus 1, this is minus of 3 amperes. Now what is this current? What is this current? So this current is I1 minus I2. So minus 2 minus 3, this is become minus 5 amperes. What is this current? This current is I2 minus I3. So 3 minus 1 is 2 amperes. What is this current? This current is I2. I2 is basically 3 amperes. Okay. So this is what the solution is. Okay, fine. I think in the same way you can do these questions as well. Okay, so let us solve this question first. So this is mesh 1, this is mesh 2, and this is mesh 3. For mesh 1, if I write the equation, so it will be 5i1 minus 3i3, right? 2, 3, 5, 5i1, and this is 3i3, because this current i3 I'm saying 3i3 is equals to minus of 6. And for this one, for mesh 2, if I ask the equations, so this is basically 5 plus 4, 9. So 9i2 minus 5i3. That's all, right? Is equals to how much? Plus 6. And the third case, this is what is my mesh 3 current I'm saying, I3. So you can see this I3 is equals to minus of 1.5 Ix. So here, what is Ix? Ix is defined here. So how do you get these currents? Now, you know, if I'm moving in the direction of I2, so this I2 is, if I'm moving in the direction of I2, that means this branch current is basically I2 minus I3. So Ix is I2 minus I3. So Ix is equals to I2 minus I3, because the Ix is defined here. So this current is this way. If I say this is basically I2 minus I3, I2 minus I3. So you can substitute this value of Ix here. So now you have 3 equations and 3 unknown. You can easily simplify them to get the value of I1, I2, and I3. And if you do it, so the value of I1 you are supposed to get is minus 3, I2 is minus 1, and I3 also it is minus of 3 amperes. So this is what the solution of this problem. Okay, so this equation you to do at your end. I am not interested to solve them. This one I think also you can easily do. So for the mesh one, if I see, so 9i1 minus 6i2 is equals to 9. This is mesh 1, this is mesh 3. For mesh 2, if I see 8i2 minus 6i1 minus 2i3 is equals to minus of 6px. Yes or no? Self is 6 plus 2, 8. Minus 6i1 minus 2i3 is equals to minus 6bx. This is mesh 2 equations. For mesh 3, I3 is anyway 5 amperes, right? Because the current source is the outer boundary, so this current is basically 5 amperes. But what is Vx? Vx is defined here. So what is Vx? So Vx is basically this branch voltage. What is this branch voltage? This branch voltage is resistance R into this current. So this current is nothing but your I1 minus I2, right? Because if I move in the direction of what? If I move in the direction of this one, so this is basically I1 minus I2. So 6 into I1 minus I2. So Vx is equals to 6 into I1 minus I2. So this you can substitute here. Then you can easily solve these equations. Okay. So if you do it, okay. So the value of I1 is 8 by 3. The value of I2 is 2.5. And the value of I3 is 5 ampere. That's what the solution. Okay. Simple problem only. Now, so this is some special case. Let's see how do you handle this special case. So now, students, if you compare this problem and this problem, so we had actually current source in the outer boundary. In other words, current source is not set by multiple meshes. In this case also, current source in the outer boundary, it is not like here which is set in 2 meshes. In this case also same story, current source in the outer boundary. But here you see the current source is bifurcating two meshes. And whenever current source bifurcate two meshes, we always make use of a concept which is known as super mesh. So when super mesh is used whenever two meshes are separated by a current source, we make use of the super mesh. So what we do is in this kind of case, so intentionally we used to skip this particular current source branch, and we used to write the equations by skipping it. That means we'll form a big mess. This is called super mesh actually. So in the highlighted part, we'll be writing the equation. So if I denote this current is I1 and this current is I2, so the equation is 12 minus 1 into I1 is minus of I1 minus 3 into I2 is equals to 0. 12 minus 1 into I1 minus 3 I2 equals to 0. This is one equation. And the second equation you can easily get by writing a KCL at this junction. So if you write the KCL, you get I1 equals to 4 plus I2. If you write the KCL, you get I1 equals to 4 plus I2. So this is what the equations. So you get two equations. Now you can simplify this to get your corresponding answer. So this is what actually called the super mesh. So when super mesh is used if we get the situations where two meshes are separated by a current source. So the value of I1 is 6 and the value of I2 is 2. So this is what the solution of this problem. And students, one thing you see, now suppose in all these problems, if I'm attaching a resistor in series with this current source, so do you think there will be change in the value of the mesh current I1, I2 and I3 even in this one? If I introduce a resistor in series, do you think there will be change in the value of I1, I2, I3? It's not, because I3 is same 1 ampere, right? We already said if a resistor is in series with current source, its current value doesn't change. The voltage and the power of this will change. Why the current will change? So even if you get a resistor in series with any current source while writing mesh equations, this resistor will not come into picture in any of the equations. And in fact, this is not going to affect the value of this mesh current. Here also same story. So if I'm writing the KCL, whether this resistance is present or not present, what it matters? This equation will be independent of this resistor. Same with the story with this as well. Okay. Now let us see this. Now, do you think here we need super mesh? Tell me, yes or no? Do we need super mesh in this case? Yes, we need. Why? Because this current source is separating this mesh and this mesh. So we need this. So what we'll be doing then? So by skipping this one, we'll be writing we'll form a bigger mesh. So this is what I'm highlighting. So in this path only, we'll be writing this equation. This is what the super mesh in this case. So the first mesh equation, this is, let's say, mesh 1. So this current, let me call it is I1. This current, let me call it is I2. And this current, let me call this is I3. Now, so for mesh 1, there is no problem. It is the same thing for mesh 1. Okay, because mesh 1 is not like it is including any current source and all, right? So the self term is 3 plus 1.5, 4.5 I1 minus 3 I2 minus 1.5 I3 is equals to 8. Okay, 3 plus 1.5, 4.5 I1 minus of 3 I2 minus of 1.5 I3 is equals to 8. This is the equation of mesh 1. Okay. Now, the super mesh is framed between mesh 2 and mesh 3. Okay. So how do you write the equation then? We can write the equation. So I'm moving in this direction. So if I'm moving in this direction, it is the reference of I3. So it is minus of 2 I3 minus of 10 I2, because here you see minus of 2 I3 minus of 10 I2. Then here, this is what? This is the reference of this I2 only, right? This is the reference of I2. So minus of 3 into what? I2 minus I1. Okay. And now if you are observing here, we are moving in the direction of I3 here. So this is basically minus of 1.5 into I3 minus of I1 equals to 0. Again, I'm explaining you minus 2 I3 because this is the reference. If you see how I'm moving, actually, I want to move in the clockwise direction like this. So this way, if I'm moving, this is coming in the I3 segment, right? So you get minus 2 I3. This is coming under this I2 segment, you get minus 10 I2. Now you see this 3. So 3, I'm moving clockwise, right? This way. So what do you think? So this way, if I move, this is the reference of mesh 1 current or mesh 2 current? Mesh 2 current, right? And if you're writing the reference with respect to mesh 2 current, what is the term you get? 3 into I2 minus I1. Similarly, here you see this is coming in the mesh 3 influence. Mesh 3 means what? I3 minus I1, right? So that's what you get. So 2 equation you get, and the third equation you can easily get by writing the KCL here. And if you write the KCL, what do you get? So you see this current is basically I3, and this current is basically I2. So if I write the KCL equation at this node, you get I3 plus 0.5 is equals to I2. I3 is equals to I3 plus 0.5, the incoming currents is equals to the outgoing currents. So these are the 3 equations. So you can simplify this 3 and you can get the corresponding answer. And if you do that, the value of I1, what you're supposed to get is 2.36. The value of I2, you are going to get this is 0.75. And value of I3 is basically 0.25. So this is what the solution of these 3 equations of this circuit. Yes, hopefully this is clear to all of you, right? This is what the concept of super mesh. So whenever we get the situation where we have 2 meshes separated by a ideal current source, always we have to make use of the super mesh concepts. In fact, there are also alternative actually. Even if you don't want to write super mesh, actually ultimately you have to write the 3 equations to get 3 unknown things, right? So in this one, if you say, so sir, I don't want to write the equation of this super mesh, I'll suggest, okay, you don't have any problem with this mesh, so you have written this. I think you don't have problem with this also. This is also simple. So some of you might have problem in the super mesh equation. If you don't want to write it, so what you do is you write the KVL in this outer boundary. Okay, so you get a third equation. So you can, by solving the third equations along with these 2, you can easily get the along with this, and you write the KVL equation of this. You solve these 3, you get again the same answer. That's what I mean. So this is what all about your mesh analysis. Okay. All right. So 5, 6 questions I have solved. Now let us see the nodal analysis. Like mesh analysis is one of the systematic technique. Nodal analysis is also one kind of systematic technique. So this is the circuit I have taken only for you, like I want to explain you. So let's call this is your what? V3. Let's call this is V4. Okay. We shouldn't be telling V3. Let's call this is V5. Yeah. So this is circuits, and I want to write the nodal equations. Nodal equation, what you have to do is you have to take one of the point is ground points. One node you have to select it as the ground points, and generally the bottom part of the circuit we take it as ground because most of the circuits the bottom part have the common segments, and if a common segment is taken as ground from calculation point of view, it is easy actually. And I already told you the concepts. If other than this, if you are taking any other point as ground, how do the node voltages changes? You know that concept. You can make use of it. So actually, like in the mesh analysis case, our goal was to get the mesh currents, and I have already shown you. If we get the mesh currents, using the mesh current, we can get any branch currents, any branch voltage. So here also the story is somewhat similar to that. So in this case, instead of targeting the various currents, we'll target the node voltages. So the node voltages we can easily get by writing the nodal equations, and that is basically KCL equations. So here what I'll always assume is, okay, so I'll write only one equations. So how do I write it? Oh, you see. So let me denote this node value is Vx is the voltage of this node, Vy is the voltage of this node, and Vz is the voltage of this node, and let's say Vg is the voltage of this node. So these are the 4 nodes, and I'll show you how do you write the nodal equation at these nodes. So always what you assume is, so by default you assume all currents are outgoing. All currents are outgoing, you assume like that. So the KCL says sum of outgoing current is equals to the sum of incoming currents. So we'll always assume the outgoing currents sum will assume, and the because so let's say this node, if I say, so to this node there are 3 branches are linking this, this, and this, and I'll assume in all these 3 branches the currents are outgoing. So if I write the KCL equation, so sum of outgoing current equals to 0 you get, because I'm assuming all are outgoing means there are no incoming. So no incoming means 0 incoming actually. So sum of outgoing currents are 0. So if I say outgoing current, this is the outgoing current direction, this is the outgoing current direction, this is the outgoing current direction. So if I write this at this node, okay, Vx, you get Vx minus V1 divided by R1, Vx minus V1 divided by R1, plus, okay, so what do you get? So this, for this branch I have written actually Vx minus V1 by R1. For this branch, what do you get? You see, so it's a current source actually whose value is I2, and there is a register actually. So you need this currents. So for this current, do you have anything to deal with this R5? It's not. So directly I'm writing here I2. So 2 branch over. And for the third branch, so this is given by plus Vx plus V5 minus of Vy divided by R2. This equals to 0. For this branch, it is Vx plus V5 minus Vy divided by R2. So if the polarity would have been this is plus, this is minus, then Vx minus V5 minus Vy by R2. So this is what is the equations of this first node, okay? So for Vx, we have done it. Now, what do you get for Vy? So Vy, if I see to this node, again, this, and this, okay? So for this one, how much you get? You get Vy minus V5 minus Vx by R2. So Vy minus V5 minus Vx divided by R2. So this is what I have written. So this current is basically the outgoing current, this one. Similarly, how much you get for this? For this, you get Vy plus V4 minus Vz divided by R4. Vy plus V4 minus Vz. Vy plus V4 minus Vz divided by R4. Minus of I1 equals to 0. See, I said sum of outgoing current is 0. So if this current is I1, there is nothing wrong to say this current is minus of I1. So that's why I'm writing here minus of I1 equal to 0. Always my concentration is sum of outgoing current is 0. So if this is I1, okay, so that means this is minus of I1. That's why, so this is outgoing, this is outgoing. So what is this balance outgoing current? Minus I1. So equal to 0. Now similarly, for Vz, how do you get? Actually, student, you see, this is the same node, right? This is the same node. Because it's a sorted path only, it's the same node. So how many branches are linked to this? 1, 2, 3, 4, and 5. So it's a big equation then, right? So let us see. So how do you get it? Okay. So Vz, okay. So one by one I'm writing. For this segment, if I ask you, so it is Vz plus V2 divided by R6. This branch is completed. For this branch, if I ask you, it is Vz minus V4 minus Vy by R4. So you get Vz minus V4 minus Vy by R4. 2 terms over. And for this, if I ask you, it is Vz minus Vg by R7. Vz minus Vg by R7. So 3 branches are over. And these are left. So for this, I3 is outgoing. So plus I3. And for this, I2 is incoming. So if this direction current is I2, so leaving current direction, this one is minus I2. So minus of I2 is equals to 0. So these are the three equations. And you will say, sir, what will be writing at VG? So for VG, actually see, the intention is to get the node voltage, this Vx, Vy, Vz, and Vc. So here, Vg, here you don't need actually any equation. Directly you can tell Vg equals to Vc. Why? Because this node voltage is same as this voltage, right? So why I need equation? So yes, if there could have been a resistor in series like this, then in that case you need some equations and all. But here, directly node itself is connected to a voltage source and to the ground then. So directly node voltage equal to this source will be V3. So this is the answer. Okay. Fine, students. I hope this is clear. So rest of the things will continue tomorrow. Okay. So you just go through this question I have just given for the practice purpose. So at any point of time, if you get doubts, so this circuit I have taken where all possibility I have taken. If you refer the solution of this problem, which is in screen now, you'll definitely get an idea. So, okay, how to write the nodal equations. So fine. So questions, it will take another 15-20 minutes, and some more gate question also I need to solve. So these things will take tomorrow, hardly 45 minutes, and we'll start the network theorems. Thank you. I'm completing the session here today.
Recording stopped.